Okay, so here's chapter 13, lesson 3. The first is a polling question. Each unit carbon in a molecule will display a blank in the 13C NMR spectrum. 13C NMRs, right? They tend to not have neighbors. So when they don't have neighbors, they're gonna have singlets. Okay. Next is gonna be it's very rare for them to have a neighboring carbon. So next is the area under the signal is or is not proportional to the number of carbons giving rise to that signal. So that's going to be is not. Okay, so it's not going to be proportional to the number of carbons under it, and that's the difference between our 13C and our 1H, right? And 1H under the curve is going to be our protons, and then our 13C does not have those under the curve, or the area under it. So next is, there are 5 characteristic regions of the 13C NMR spectrum. Complete the diagram below by placing the types of bolded carbons below into the appropriate region of the 13C NMR spectrum. So this is what it's going to look like. The way you can kind of remember this by is that the sp3s are going to be the most shielded, right? They have, and so most shielded, so lowest frequency. Because think of sp3s as just being kind of weak, right? It's just one bond. What's it going to do? Nothing. Next is, I think of it as electronegativity is increasing. They're going to be here, like N, B, R, and Cl. However, the oxygen that's right next to the fluorine is going to be a little higher, right? But then here we have a carbon triple bond. So, and here you see that there's a carbon double bond right there, but the difference between them is that there's 2 pi bonds here, which is there's 1 pi bond here, and that is increasing the electron withdrawal, right? Because there's only 1 pi bond, it's going to be increasing electron withdrawal. Here, there's 2 pi bonds, and the 2 pi bonds are there kind of helping one another. Okay, the 2 pi's are helping one another, and they are making them stronger. However, here, there's only 1 pi, so you can think of it as more like radioactive in a way. It's all alone, and so it's really pulling in density, which is what makes the frequency for this one higher and more deshielded, because there's just 1 pi here, and that's what makes this one less frequency and more shielded, is because there's 2 pi's that are helping each other. Okay, and then the benzene ring, you can kind of just think back to the other one, is that it's just there, bruh, like, yeah. Then you have the COs. Remember what we said here, right? The reason that the frequency of this is higher is because of that 1 pi bond. Here we have the 1 pi bond, and we have that oxygen. So it's a double whammy, okay? So you have the 1 pi and you have the oxygen. So those are going to lead to carbon double oxygen being the highest. Okay, so next is these, and I'm going to go through these with you. It's pretty much asking how many unique carbons are going to be there. So here, what's the first thing you noticed? And keep in mind, remember, the 1H, how you find the signals is the same as how you find the signals for the 13C. Okay, so what do you notice here? You're going to notice that there has to be a mirror plane, right? There's a mirror plane this way. Is there another one? Yes, there is. There's another one that's going this way. Okay, so when you have 2 mirror planes, what's that going to tell you? For example, let's start with this, because I literally just messed this up. When it's like this, we're not going to include these as being equals, right? Because they come onto the mirror plane. However, because we have a mirror plane that's going this way as well, we do say that these are going to be their equals. Because this one is A, this is A, B, B. Because in this one, it doesn't have the mirror plane on here, since we have 2 mirror planes, right? So now, we could say that, oh, with this 1 mirror plane, this is going to be C, this is going to be C, and then this is D and D. But that is not true. because we have that mirror plane, that second mirror plane, that's going to go this way. And when we have that second mirror plane, we're saying that everything on the ring is going to be equal to one another. So we have A, B, C, 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 C. Okay? So the reason that these B's are not the same, even though they're on the ring, is still going to be because of this right here. Right? So if this one is here, we can't say that these are equals of this. Okay, it's because of the two mirror planes. Okay, however, because there's a mirror plane here, we can say that these sides are equal to one another. Next is going to, so this is going to give us 3 signals. Next is B. So what's the first thing you notice here? There is a mirror plane. You split this in half, right there. Is there another mirror plane? No. We can't do that, it wouldn't be equal. We can't do that, it wouldn't be equal. So there's only one mirror plane in this. So we say that it's going to be A, B, B, right? A, B, B, C, C, and because there's a mirror plane right here, this is going to be D and E. Because remember, anything that's on the mirror plane are going to release their own signals. Okay, so how many is that? This is going to be 1, 2, 3, 4, 5. That's 5 signals released from here. So let's just put 5. And then C. What do you notice? You're going to notice another mirror plane. Okay? The mirror plane is right there, meaning, what are we going to have? And again, we only have one mirror plane, right? That wouldn't work because you can't flip these over. They have nothing to match them. So we're going to do, this says A, right? Because these are equals. Then B, B, because those are equals as well. C, C, D, D. So that's going to be 1, 2, 3, 4 signals. This is going to release 4 signals. Next is this one, and if you remember, this is like the same as we did in the hydrogens. So first, let's consider this right here, okay? And let's use this down here. So we see that we have a signal at 200, meaning we have to have a carbon double bond in here. And that's what we have, right? Or our molecule that we're looking for has to have a carbon double oxygen bond. Then we have 2 signals here, meaning it has to have either a carbon double bond or a benzene ring. So we labeled that 2 carbon double bonds or a benzene ring. Next are going to be these, right? Which are between 0 and 50. So 0 and 50 meaning no carbon triple bonds and no carbon oxygens, but we can have a carbon nitrogen, carbon chlorine, carbon Br, or an sp3. Okay, so well, we won't reveal that yet. So up here, what do you notice about this structure right here? First, we need a carbon double oxygen bond. It has that. Next, we need 2 carbon double bonds or a benzene ring, and we have that. So, however, there are 4 signals that are going to be coming from the 150 to 100 range, and we only have 2 signals here. So, what's it called? Let's split this, right? We can split it this way, and that gives us these 2 sides as being equals. We can't split it this way because it has this whole thing attached to it, and there's nothing on this side, okay? So we say that there are going to be there is A, B, B, and C, and D as the signals that are arising from here. So that is 4 signals in the 150 to 100 range. So this one wouldn't work, right? This is not one of our answers because we only have 2 signals in the 100 to 150 range. So let's move on to B. What do you notice? We need a carbon-oxygen double bond. We have that right here. We need 2 carbon double bonds or a benzene ring. We don't have that, so we can't use B at all. Okay, so we don't consider it because the ring has no double bonds and our spectrum has 2 either double bonds or a benzene ring. This does have the ring, but it doesn't have the bonds. Okay, next we consider C. So in C, what do you notice? Well, first, we don't have a carbon-oxygen, so right off rip, like that's wrong. We do have a carbon double bond, but we only have 1. And this one has a triple bond. But on our spectrum, we have no triple bonds. A triple bond would be between 50 and 100. We have nothing lying between 50 and 100. So we also don't consider C. Let's take a look at why D is correct. First, let's start off with C, the carbon double oxygen bond. We do have that right there. Next is the 2 carbon double bonds or a benzene ring. Okay, so we have a carbon double bond right here. And on that carbon double bond, we're going to have, on that carbon double bond, we have 2 carbons, right? So that means that 2 carbons, because they give off separate signals, we're going to get 2 signals that are of equal length or kind of frequencies right here, okay? So this gives rise to our 2 carbon double bonds. So we can color that as, let's label, right? So our dark blue is going to be our CO, our yellow or green. Next is going to be this one right here, right? So our CH, let's start putting in the H's. So right here, our H, we only have 1 H, which makes sense as to why I would have the next highest frequency. Here we have CH3, CH1, CH3, CH3. Okay, so next we have these 2 right here. Right, we want to know the difference between them because they're both kind of, let's just say 2 bonds away. Right, they're both 2 bonds away. They are equidistant from one another. Which one do you think is going to be more deshielded? It's going to be the CH1, right? So our next one, the purple, is going to be CH1. And then our red is going to be CH3 because it's the next in line. And our final one are going to be the CH3s. But then we have an issue, right? We say that this has 7 distinct signals. And it is 7 distinct signals because, oh my god, there is a carbon-carbon bond rotation here, meaning that we have purple here, and then these are going to be equal, right? They're going to give off the same signal. So those give off 1 signal, and that puts them right there. And the main purpose is to use this to identify what the signals are, and then use process of elimination to get rid of these. Because again, this one has a triple bond. It does have the double bond, which gives off the 2 signals, but it has a triple. This one has no doubles, has the carbon-oxygen. This one gives off 4 signals. Like, everything is perfect in this, right? Besides the fact that it gives off 4 signals from the 150 to 100 range, and we only have 2 signals there.